Hello everyone, we are Group 9, and today we are going to introduce our ODE midterm project. And our topic is about measuring time using RC circuit. Let's begin with our introduction. There are many ways for people to measure time. The easiest way to know what time it is might be watching the clock. And in ancient era, people might use hourglass to measure time. So the common things in these two items are that they all have a time constant. Like in a clock, the finger of the clock might move around the clock for every 60 minutes. For hourglass, it will also take a certain amount of time for the sand in the hourglass to completely leak out. So why we are using RC circuit as our model? It's because the features that are observed in an hourglass and a clock can be also observed in the RC circuit. Actually, RC circuit is a simple circuit that contains a resistor and the capacitors, and it can also display oscillation. It also has a time constant. So let's further analyze RC circuit using some mathematical ways, like ODE, which we learned in this semester. So this is an RC circuit. So there's a resistor and a capacitors. So how do we express this circuit in a more mathematical way? We can use the KCL, and we can get the first equation. The first equation just tells us that the voltage across the capacitors will equals to the voltage across the resistor in this circuit. So we get Q over C will equals to I times R. And we can also, from this circuit, observe the second question that negative dq over dt will equals to I, which means the small amount of change of the charge on the capacitors will equals to the current flowing through the circuit. And if we combine the first equation and the second equation, we could get a third equation that dq over dt will equals to the negative 1 over RC times Q. And this is a simple differential equation. We can integrate both sides with dt, and we could get the last equation. The charge on capacitors at any time will equals to the initial values of the charge on the capacitor times an exponential terms. So the last equation just suggests that this circuit has a time constant. We'll need to charge or discharge the capacitors in this circuit in a certain amount of time. So what is happening in the RC circuit is plotted. So from this plot, we can see that the x-axis is time and the y-axis is voltage. If we constantly switch the power supply between on and off, we can see that when the power supply is on, the voltage across the capacitors will increase exponentially and reach its peak value in a certain amount of time. And we can also observe that if now we turn off the power supply, the voltage across the capacitors will also decrease, and it will decay to its initial value also in a certain amount of time. So from this circuit, so from this plot, we could see that the RC circuit has the potential to measure the time because it has a time constant. It requires a certain amount of time to discharge and charge the capacitors. So the above mentioned are the basic concepts of RC circuit, and next we are going to display our Python simulation.
Hello everyone, so today I'm going to be introducing the Python code for our midterm project. So first I'll briefly go over what exactly we're trying to do. So our group is going to be using RC circuit to be measuring time, specifically using the charging and discharging properties of it. And what we're basically trying to do is find time constant tau. So first step of the code is to import the libraries that we're going to be using as usual. So we have NumPy, SciPy, Matplotlib, and next we do SciPy.signal because our input waveform is a signal, output is also a signal. So we need something to plot it, to plot the signal. And then we also have from SciPy or SymPy import init session, which what this does is it imports the entire library instead of a specific function or like an operation. Okay, so here we're gonna write the ODE in terms of time. So T is time, Q is input signal, and then X, and Y is the output signal. And we also have R and C, which is resistance and capacitance. So here we have our ODE, which is U of t equals to R times X of t, and then times D of dt, plus 1 over C, 1 divided by C times X of t. And then Y of t equals to 1 over C times X of t. Okay, so we have an ODE where we could solve it directly, but that's not very useful. So what are we going to do? So we could change this to frequency domain and find the transfer function of the circuit. And okay, what is the transfer function of a circuit? What the transfer function is, it's basically the ratio of output signal to input signal, which is just y to u. Okay. Oh, and it's in frequency domain, and it's important because, as I stated, at first we only have our ODE in terms of time, so we need to be able to change the time domain to frequency domain. So we can do this by either using the Fourier transform or the Laplace transform, and we're going to use Laplace transform. The reason for this is because Fourier transform um, is doesn't apply everywhere because some ODEs end up having they expand to infinity, so the Fourier transform for those functions don't exist, whereas the Laplace transform is generally applicable to every function. Okay, so we'll write everything in terms of s, which is another variable, which is similar to how we write time here. So we have u, x, and y again. And then here we have our ODE, which is u of s equals to r times s times capital X of s plus capital X of s divided by c. And then y of s becomes x of s divided by c. So if we compare the frequency domain ODE to the time domain, we can see that it's actually quite similar. So x of t becomes capital X of s, whereas the constants c and r, which are time independent, are just the same. So they are treated as constants and they remain the same. And then here, 1 to d of dot is becomes, or sorry, 1 times d divided by d of t is s. Okay, so we have a frequency domain, ODE. So mathematically, we don't actually have to solve for y because we already have it, but Python doesn't know. So we actually have to solve it using solve. But mathematically, we can divide by, or do y divided by s, which will just give us the transfer function because that's what we said, the ratio of output signal to input. So we find that it's 1 divided by c times r times s plus 1. Okay, so we have an expression for the transfer function. We can use simpy.poly to change it to a polynomial. And what we can do is we can write this as an array using the for loop. So we have two arrays, num and den, which denote the terms of the polynomial. And then we end up with a transfer function array, which is our output signal. Okay, so this is the resulting waveform that will display the charging and the discharging of the RC circuit. Okay, and then we can set the value of R and C, which here I set as 100k ohms and 0.05 microfarad respectively. And then we have to substitute this into the transfer function because here it's dependent on R and C. Okay, and then we can set the t, which is the time or the period that we want to observe, and we also can set the input signal, which is generally a square wave. Yep, and then here's the square wave that I set. It's just a random one, and then we can plot it. So here is one cycle of the signal, and then the orange denotes the signal for the charging and discharging. Here is charging, and then here is discharging, and then the blue obviously represents the input signal, the square wave. So what we can do with this is we can measure time because this to this it's half the period. So we can use this to this to measure time, like when it's charging or when it's discharging. And then here it's just the same waveform, but it's observed over a longer period of time, or like more cycles. Yeah.
Hello, my name is Chen Jia. I'm going to talk about how we plan the physical realization on our midterm project. At first, we will compose a basic RC circuit. What is RC circuit? RC circuit is a circuit with resistor, and capacitor. And we will also add a voltage source here, create a square wave. Okay, capacitor is our main component in the circuit. Because we use the feature of it, the capacitor will charge and discharge, which will cause the different voltage output here. Okay, let's talk about the basic function of our clock. Our basic function is to record the time. We will wire the IC555 to our circuit and wire the 7-segment display to the IC. And because the output voltage will change by the time, which will cause the IC have different work, and will also cause the 7-segment display show different number. And where we finish our experiment, we will compose our circuit. We will go to the electronic laboratory to do it. Okay, after we have some results, we will add the transistor to our basic circuit, make it more advanced. advanced. And this photo is I found on the internet. It is circuit in the real clock with transistor. Transistor is here, and we can find that many clock we see in daily life is based on the transistor circuit. Okay, next part we'll talk about something we simulate on LT-SPICE. By the way, LT-SPICE is a software to simulate the circuit, and it is widely used.
Hi, I'm Dong, and today I'm going to introduce our simulated circuit in LT-SPICE. And we can see that here we had a RC circuit, and we input a square wave in this RC circuit, and we make the RC circuit to determine our time range by the time constant RC. So the size of the capacitor and the resistor will impact our time range size. And in the simulated figure, we can see that the red line is the input square wave, and the blue line is the output wave. And how do we determine our time range is that when the output voltage is grew up and at the same level of the input voltage. At this time, we say that this is our time range, and by this way we can make sure our every time range is same and stable.